So it's a pleasure to have Yash Narang visit us today. Yash and I actually met kayaking in Australia, and and Yash just look at his shoulder. It's a wild time, and so it's interesting that we're in Seattle together now,
Yeah.
so many miles away. But since then, Yash has been at NVIDIA doing some of the most exciting work in assembly, in sim-to-real, behavior generation, and he's going to tell us a bit about the work at NVIDIA on factory. So take it away.
Thank you, Abhishek. That's right. So today I'll be talking about our sim-to-real journey over the past few years in contact-rich manipulation, with a special focus on robotic assembly. So I'm happy to answer any clarification questions as we go through this, but I'm also going to try to cover a lot of ground. So any more detailed questions we can always address at the end. So in this talk, I'll start by motivating our research effort. I'll then discuss how we've addressed open challenges in simulation, sim-to-real, and multimodal sensing, all applied to robotic assembly. And finally, I'll summarize both the takeaways and the limitations, and I'll mention some next steps that we have in mind. All right, let's get started with the motivation. So what is robotic assembly? I'm sure most of the audience is already familiar with the topic, but I'll run through some definitions and define our scope a little bit. So assembly itself is simply the process of putting mechanical or electronic parts together. It actually involves a diverse set of sub-processes, but we focused on the mating and joining process since that's the most difficult to automate. This process can actually include many different operations like peg and pin insertion, electrical connector insertion, nut and bolt fastening, and so on. And finally, robotic assembly is simply the process of using robotic arms, grippers, and hands to perform these operations. Some examples of assembly tasks on the right. So what's missing today in robotic assembly? Let's first look at the industrial setting. So modern assembly lines are typically based on a fixed automation paradigm in which each system performs a specific task in a specific environment. These systems can achieve high precision, accuracy, and reliability. However, the systems often require expensive hardware, custom tooling and fixtures, long setup times to calibrate the robot, design the tooling and fixtures, manually design trajectories, and tune controllers. And most importantly, the systems can also be highly sensitive to variation in part type, location, appearance, material properties, and so on. So this paradigm is well suited for large-scale manufacturing, but not ideal for small and medium-scale enterprises, which typically need to manufacture parts in low volumes, often with frequent changes to their assembly lines. Now let's look at the research setting. So in recent years, the research community has moved further towards the paradigm of flexible automation, in which systems can manipulate multiple objects in less constrained environments. So these systems are often more affordable than industrial solutions and can achieve slightly higher adaptivity and robustness. At the same time, these systems can also be slow and have low or unclear reliability relative to industry standards. In addition, they often have similar weaknesses as industrial methods, such as customized tooling and fixtures, long setup times, and still often a relatively high sensitivity to variation. Finally, why is robotic assembly important? So assembly is found everywhere in several major industries, including automotive, aerospace, medical devices, electronics. It's been difficult to find data on exactly how big the assembly automation market is, but one estimate has it at roughly $52 billion today, growing to over $100 billion by 2032. And what might also be surprising is that the majority of assembly operations are manual, including almost any task that encounters significant variation in parts or the environment. So as a fun example, I'd recommend taking a look at the beautiful videos on YouTube where drones fly through Tesla Gigafactories. And these factories have some of the most advanced automation systems in the world. But once you reach the general assembly areas within these videos, you'll see that humans are prevalent once again. So hopefully I've convinced you somewhat that robotic assembly is both challenging and valuable. But how did we come to believe that research could actually add real value to industry in this domain? For context, the most established benchmark for robotic assembly is the NIST assembly task board, or series of task boards, which is shown on the top right. The first one consists of different peg insertion, connector insertion, and nut tightening tasks. In early 2021, there was a collaboration between Google X and DeepMind that really caught our attention. So the researchers selected 3 tasks from the NIST board. They manually collected demonstrations, and they trained an RL policy purely in the real world with human corrections. They used DDPG, which, as many of you know, is a model-free off-policy RL algorithm, but they incorporated demos into the replay buffer. Their work did have limitations, which I list here, but the remarkable part was that they compared their solution against 2 professional robotics integrators and showed that they could be more robust to object perturbations along X, Y, Z, and yaw. And these results suggested to us that there could actually be significant real-world potential in RL-based solutions for robotic assembly. At the same time, we felt that relying on a combination of human demos, real-world RL, and human corrections could be difficult to scale. But there was an alternative paradigm emerging, which was doing simulation-based RL, followed by sim-to-real transfer. OpenAI had recently done groundbreaking work on robotic hands, where they used MuJoCo to train RL policies to manipulate a cube, and then transferred the learned behaviors to the real world. And there was ongoing work at ETH Zurich and NVIDIA on quadruped locomotion using similar techniques. NVIDIA as a company has always aimed to be at the forefront of accelerated computing and simulation. And so we wanted to leverage this strength in our research, and essentially we made a bet that sim-to-real would eventually work and be truly useful for robotic assembly as well. So I'll begin the main part of the talk now, where I'll discuss our sim-to-real journey. And of course, before you can even use simulation to train RL policies and attempt sim-to-real transfer, you do need a simulator. There was no out-of-the-box solution to simulate contact-rich interactions present in robotic assembly. So our first task was to help build one. This work is fully described in our factory paper from RSS 2022. Okay, spinning wheel. Okay. So you might be wondering, couldn't we simulate contact-rich interactions already? We definitely could. There's been a lot of great work out there, both on the analytical side and the graphics side, but there were limitations. So consider the problem of simulating a nut and bolt. This is a canonical problem for assembly, as approximately 40% of all mechanical assembly operations involve threaded fasteners. Despite their prevalence, it wasn't previously possible to simulate them faster than real time. What's hard about it? There are finite clearances between the threads of the nut and bolt, shown in the bottom left, the cross-sectional view. And these clearances can allow the nut to actually move with 6 degrees of freedom. In addition, triangular meshes of these parts might consist of over 40 or 50,000 elements. And it's a major computational challenge to detect collisions between these meshes, generate contact points and normals, and ultimately solve the associated non-penetration constraints. So as a result, okay. Let me see if get past this lag here. Okay. Yeah, so as a result, the fastest simulators at the time could only simulate a nut and bolt interaction between 1/350th and 1/20th of real time. Yeah. Yes.
We'll talk about this later.
Sure.
But, is the challenge establishing true contact, or is it simulating forward through the contact? Like, is it hard to tell where the contact occurred, or is it hard to tell? Is it hard to like forward simulate the model, or probably both? But
it's
like,
both. It's actually both.
Where's the most of the mass? And if you're going to talk about it later, I can also.
Yeah, I'll go through it, but yeah, the quick answer is it's both. So it's hard to first of all determine where to generate these contact points and normals, and second of all, there's basically limits that you hit. For example, the limits that we experience are on GPU with how many contacts you can essentially attempt to solve simultaneously. So it's kind of.
And you are committed to a mesh-based representation rather than like SDFs or something.
I'll go through that actually. Yeah. So yeah, this is actually what's the right representation. So when we started on this problem, we evaluated several geometric representations that could be used for highly detailed objects like you see here. And for example, for a bolt, a convex hull clearly doesn't accurately describe its geometry. And convex decompositions with a large number of convex shapes might appear at first to faithfully describe geometry, but close-up inspection, even with state-of-the-art algorithms, reveals spatial artifacts. And even for perfect decompositions, collision checks can be expensive, and undesirable contact normals can be generated. So triangular meshes, of course, can faithfully describe geometry and are often used as ground truth for geometry. But again, collision checks are expensive, and interpenetrations between objects can be difficult to resolve. For example, getting accurate inside-outside information. Yet another representation not shown in this slide are tetrahedral meshes, which can be used, for example, in combination with the finite element method. But these sort of techniques often have a much higher computational cost. So after experimenting with several approaches, my best result here, oh, that's not the one. Okay, it's very laggy to step between these videos, so you'll just have to trust me. That simulation on the left is a very slow simulation. It executed in 1/80th of real time. So I actually discussed the problem with someone named Miles Macklin. He's a simulation engineer at NVIDIA who now leads the Warp team. If you haven't used Warp before, you should definitely check it out. It's amazing. And Miles, at that time, had recently gotten phenomenal results at simulating cloth interacting with rigid bodies. So I wish I could. There we go. OK. So the cloth in rigid bodies had tens of thousands of elements, but there were almost no interpenetration artifacts between them. And the key insight was to use signed distance field representations, as well as an optimization procedure. So I show an example SDF to the right. And as I'm sure many of you are familiar with, an SDF is simply a map from any point in space to its signed distance to a surface. And with high resolution and interpolation schemes, SDFs can very faithfully represent detailed surface geometry and provide reliable inside-outside information. In this case, he represented the cloth as a mesh and the rigid body as an SDF. And for now that slow simulation is playing, that's great. For each element of the cloth mesh, he queried the rigid body SDF and performed a local first-order optimization procedure using projected gradient descent and Frank-Wolf to determine the closest point on the cloth element to the rigid body. And he then used these closest points as contact points where non-penetration constraints were later solved. Since SDFs can be pre-computed and stored as 3D textures, which are hardware accelerated on a GPU, these distance queries and interpolation operations can be extremely fast. Miles and I spent some time adapting this technique to the highly detailed contact-rich scenes I was interested in simulating for robotics, and ultimately we got exciting results. So using SDFs, we were finally able to achieve the first real-time simulation of a nut and bolt, and as you can see here, I'm interacting with this via mouse springs. And here I show two other tasks from the NIST benchmark, which is a set of spur gears and a D subminiature connector with 25 slender pins. So we then progressed to simulating the entire NIST benchmark in a single scene. For reference, I show the physical benchmark again in the top right. And I'll just let this play for 5-10 seconds.
Another quick question about friction. Mm-hmm. Are there certain effects that occur at certain coefficients of friction around, like jamming and all of that, particularly when you have insertion?
Yeah.
And those can be, obviously, Coulomb friction itself is non-Newtonian, mm-hmm. hard to simulate. How do you consider that? How do you resolve it?
Yeah, so basically the core solver behind PhysX tries to address the full NCP with the Coulomb constraints and so on. And with regard to jamming, these are things that we actually observed in simulation, often during RL training that it sort of learned to avoid. Hopefully, I won't show an example of jamming, but I will show some interesting contact effects later on. So,
yeah. Kind of related question, which is, I assume so you can predict forces with this.
Yes.
Could you check if they're correct?
I'll actually show a slide on that not too long from now. So I should note that we hadn't actually achieved our goal just yet. The research efforts from OpenAI, ETH, and NVIDIA that I mentioned earlier We're using model-free on-policy algorithms like PPO. Okay, great. Yeah.
Hi. So one question I have is there are contact implicit representations and contact mode representation. So in this simulator, what is the representation that is used? Maybe I missed this in the previous slides.
The geometric representation, so SDFs, right? So basically every interaction is a pair of SDF and a triangular mesh. And essentially the mesh is queried using the procedure I talked about earlier against the SDF. And the opposite operation is also performed where the second object is represented as an SDF and the first as a mesh. Yeah. So since these algorithms are highly effective but sample inefficient, the researchers in these studies needed to parallelize interactions across hundreds or thousands of environments. And we had only focused on a single environment thus far, so we needed to do a bit more work to make our approach scale. So let's return to the canonical problem of simulating a nut and bolt. Collisions between the nut and bolt here might generate 16,000 contacts. And as a result, due to memory bandwidth limitations on a GPU, we could at that time only simulate 20 nuts and bolts in parallel in real time. Our intuition was that not all 16,000 contacts were actually needed. They could likely be greatly reduced while having no observable effect on object dynamics. We discussed this hypothesis and this problem in general with NVIDIA's PhysX team. And as it turns out, they had actually been working on contact reduction algorithms, primarily heuristic, since at least 2004. And their latest implementation processed contacts in batches, assigned contacts to contact patches based on the similarity of normals, and then culled contacts within those patches based on their penetration depth and area coverage. Together, we spent some time adapting this technique to our robotics scenes, and again, we got some good results. So for the nut and bolt, we could reduce the 16,000 contacts to just 300 with minimal loss of accuracy. And as a result, with either a Gauss-Seidel or a Jacobi solver, we could simulate 2 orders of magnitude more nuts and bolts in parallel in real time. So I'll show some examples. So this is 1,024 nuts and bolts in parallel in real time. This is 512 bowls falling into a pile in the same environment. And what I also like about this is one journalist seemed to really be fascinated by this. So we also simulated 60 chairs falling into stacks in the same environment. And most importantly for our mission in robotics, we could also simulate complicated scenes involving robotic manipulation. So here, nuts are dropped onto a vibratory feeder plate, vibrating at 60 hertz, although you can't see it. These mechanisms are often used in manufacturing settings to singulate parts. And a robotic arm then executes a scripted trajectory to grasp the nut and tighten it onto the bolt. And we simulated 128 instances of this environment in real time. So with our fast contact simulator at hand, we now turn to training RL policies. So to begin, we approached NVIDIA's Isaac Gym team, now the Isaac Lab team, who helped bring our simulation methods into their robot learning software. We designed realistic assets based on the NIST benchmark, created learning environments, and implemented a tensorized suite of commonly used robot controllers.
Another quick
Yes.
question. I'm
Yes.
so sorry. In the previous slide, so you have 60 simulation assets, super impressive. If I wanted to add more assets, like what does one do? Again, if you're going to talk about it later, we can discuss.
Yeah, I don't discuss this particular point later. I will say that the assets that are available online, so if you, for example, purchase mechanical parts from McMaster or electronic parts from DigiKey, you might be able to get 3D CAD models from those places. And that's a great starting point, but it's not the ending point, because they often don't accurately model things like clearances and tolerances. So the procedure here was essentially trying to start with as many of those as possible, looking at data sheets and specifications, and then making adjustments in CAD software, quite manually, to be honest, to get very realistic versions of these assets. I don't think this is a scalable way forward.
Then I guess like once you have a realistic 3D model, then everything that follows, like generating the SDFs, and then generating the contact reduction, all of that is like automated?
That's automated.
Okay.
One of the few parameters that you might want to tune is maybe your SDF resolution, which is essentially the number of voxels in your sort of 3D voxel grid that extend along the long axis of the object. We typically keep that number the same for every one of the objects that you see here. So it's pretty minimal tuning. Yeah.
And are these assets like purchasable? Surely somebody has.
Yes, they are purchasable. So yeah, so all of these nuts and bolts are purchasable. The electrical connectors, like if you actually look up the repo for this, you will see the links to the DigiKey, for example, websites where you can actually order these parts. Yeah. So we then return to our canonical task of nut and bolt assembly. We divided the task into 3 phases: pick, place, and screw. Learned a policy for each, and then executed the policies in sequence. I won't go into too much detail now on how we solved each phase because I'll cover similar topics later. But for now, I'll mention that we used a GPU-based implementation of PPO and did a systematic study of our MDP formulation to identify the most effective observations, actions, and rewards. So this was our initial result. And this was the first evidence that we were familiar with, at least, that you could train a robot in a simulator from scratch to learn these kinds of contact-rich behaviors.
Is it actually vibrating it to stick it in? That's a very common technique that's used.
Yeah, technically that was a vibration, although I do wonder if that was it being intelligent or whether it was perhaps a little bit of controller instability there. Yeah.
Yeah, it's a common trick that's
Yeah.
used.
I'll actually show something later that it's kind of this backspin first technique when you're threading fasteners together, which kind of emerged in a later stage of training. So question of forces. So we often get a question about how accurate the simulator is, and I actually think it's a fairly deep question, and I'd love to talk about it in detail afterwards. But I'll just quickly mention that we did also evaluate whether forces and torques were realistic. So we rolled out a trained policy for the screw phase of nut and bolt assembly. And we found that the simulated contact forces, if you look at that plot on the left, were contained within the real-world distribution, and that robot joint torques on the right were within the range of real robot arms if you were to look at these data sheets, even for a UR3, for example. So what could we do now? We could simulate contact-rich interactions, often much faster than real time, and we could use the simulator to learn plausible RL policies for assembly, including with these data-hungry approaches. Okay, so I'll now move on to our research on transferring these learned behaviors from sim to the real world. I'll start with part 1, which is our proof of concept that this was possible for robotic assembly. And this work is described in our industrial paper from RSS 2023, led by interns Bingjie Tang and Michael Lin. Okay, yeah, so this is, I'll actually show another duplicate of this video later, so we'll get to that. So before I begin, I'd like to just recap why sim to real is challenging. It isn't always obvious unless you've tried it firsthand. First, there are perceptual discrepancies between simulation and the real world. Simulated sensors such as RGB and depth don't perfectly replicate real-world behavior. Second, simulated physics models might, of course, not exactly model the physics of the real world. Third, even with perfect physics models, parameters of the models may be unknown, might require careful calibration. Next, even with perfect physics models and parameters, there are always computational trade-offs between simulation speed and accuracy that need to be considered in order to use data-hungry algorithms. And in the real world, sensor signals, actuation commands, and neural network inference typically happen at distinct frequencies with varying degrees of latency. And finally, when learning a skill in simulation, it's essential to evaluate it frequently in the real world. And this often requires time, effort, expense, and so on. Okay, back to the problem at hand. Let me describe our real-world hardware and our tasks of interest. So we have a Franka Panda robot with a wrist-mounted RealSense D435. Below the robot is an optical breadboard used for placing or mounting components. And although we previously learned policies for nut and bolt assembly in sim, we started our sim to real effort with insertion tasks, as we believe these to be less complex. We designed peg and hole assemblies, electrical connector assemblies, and a 3-gear assembly, all adapted from the NIST benchmark. And you can actually, this is all publicly available, so you can just reproduce these assets. We initially used our methods from the factory paper to train simulation-based policies and tried deploying them in real. Unfortunately, we actually had very little success, often due to discrepancies in dynamics and control. For a couple of examples, in our original simulation work, we used an operational space motion controller, which assumed that we had access to an accurate inertial model. We didn't have such a model in the real world, so we had to take a different control approach. Our simulations often had friction, damping, and other energy dissipation mechanisms in order to ensure that the robot's motion was smooth and that contact was stable. But these mechanisms weren't always grounded in real-world measurements. So when we deployed simulation policies in the real world, the robot displayed unsafe behavior, and when we increased the realism of our simulator, we struggled to train policies. So ultimately, we needed to do a bit more work. For sim to real, we defined success here as achieving at least 80% success rates in the real world, while being robust to randomized part poses, perception noise, and control error. Of course, 80% is not enough for industry standards, but it was our starting point.
On the previous slide, you had gains.
Yes.
What did that mean?
Just controller gains for the operational space motion controller and for the task-based impedance controller.
Just the values were off.
The values were quite a bit different. Even for any particular controller, kind of the starting point for tuning these gains in real was actually quite a bit different from our assumptions in sim. So to accomplish this, we developed 4 techniques. We used 3 of them during simulation-based training, and we used the 4th in the real world. And the number next to each indicates how much success rate dropped when we removed that particular technique. So I'll just discuss the 2 methods in green, since those might differ the most from standard approaches. So let's start with a simulation-aware policy update. So although our simulator could effectively simulate contact, again, we're always making trade-offs between speed and accuracy, for example, through contact reduction or through tuning solver iterations. And this always results in a very small amount of interpenetration error between objects. So on the left is a typical peg and hole assembly, and in the middle is a histogram of errors during simulation. Although the errors are small, they can actually be the same order of magnitude as the clearances between parts, so they matter. Our realization was that these errors can actually make it quite challenging for a simulated robot to solve the problem, especially because they're often stochastic. We therefore proposed a simple procedure of computing interpenetration error between objects at each time step using warp, filtering out highly inaccurate time steps, and weighting the reward at remaining time steps to penalize interpenetration. This procedure is very simple, but it turned out to be highly effective, and we believe it's kind of initial signal on a more general idea, which is that whenever possible in sim to real, simulator error should be quantified, and policy learning should be explicitly or implicitly guided by this information. So let's talk about the policy level action integrator, which we use at deployment time in our robot.
Quick question about
Yeah.
slide.
Yes.
Can you go back?
Yeah.
So if you wanted to actually measure where the simulator was wrong, wouldn't you have to go to the real world and go back, and isn't that
So
painful?
so in general, that's correct. With regard to contact simulation in this context, we assume the real world cannot have interpenetration artifacts. So essentially that value is always 0, right? Yeah. So policy level action integrator, or PLAI. So as a very simple example, consider a reach task where a robot has to move the center point between its fingertips to a target. On a real robot, there are many physical effects that are difficult to identify, model, and calibrate in simulation, such as imperfect gravity compensation or unmodeled joint friction. And with a standard RL and control approach, the robot might never actually converge to its goal under such disturbances. And this issue created significant difficulty for us when deploying policies for any task on the real system. So I'll go ahead and explain the method. So the most common RL approach for robotics is to interpret actions as delta state updates. What we proposed instead was to apply actions to the previous desired state. If this isn't immediately intuitive, it's actually equivalent to defining the desired state as the initial state plus the sum of all actions over time. And thus, as the name suggests, PLAI simply acts as an integrator over policy actions. And in that sense, it's actually quite similar in spirit to classical PID control, and it's very effective for reducing steady state error in the presence of disturbances. But PLAI empirically produces better performance, which we analyze in further detail in our paper. So I'll show some of our sim-to-real results. Here was an initial experiment to test whether we could do sim-to-real of RL policies that simply move the robot to grasp and transport parts. We placed various pegs and gears in front of the robot, and we placed small labeled bins in front. We detected all the parts from RGB images and deployed policies that were trained to grasp and transport the parts anywhere in the workspace. The system was able to sort all the parts, although I don't, and there's a question back there, yes?
Sorry, I guess I'm missing some context here on the manipulation. For these tasks, is it assumed that all you need to control, or the policy just has to move or is the policy only for the end effector? Or
The
do you
policy-
also have to produce IK solutions for your entire...
This is all in task space. Yeah, this is all in task space. So the policy actions are delta states, where states are basically the end effector pose. Yeah.
Thank you.
So yeah, although I don't show it here, the robot could actually be physically shoved during this motion as well, and it could quickly recover. So we do have a significant speed up on some of these videos. And this is primarily because we've been highly conservative about our control gains and action scales to prevent damage. And as we've gained confidence in our approach in recent times, we've been able to relax those thresholds and achieve faster executions. So we then evaluated whether we could do sim-to-real transfer of RL policies that actually assembled the parts, assuming that one of the parts was already pre-grasped. So we bolted receptacles to randomized locations, randomized the location of the gripper above the socket, applied artificial observation noise, and then executed policies. And the system achieved success rates of 83% over all trials. For high levels of noise, the policies often exhibited an emergent searching behavior. And just to note, the electrical connectors, the small and large gears, were actually never seen during training either. And finally, we evaluated whether we could do sim-to-real of RL policies that actually combine these things, grasping, transporting, and assembling the parts from start to finish. So the parts were no longer pre-grasped. So again, we placed the parts in front of the robot on the board. We detected all the parts from RGB and deployed our RL policies on each part. And the system achieved success rates of 89% over all trials, with near perfect performance on the gears and connectors. And so this was the first demonstration we had seen of sim-to-real for sort of this start to finish assembly task without involving real-world adaptation or fine-tuning. So the takeaway from this part is that we could actually transfer RL policies to the real world. And I'll proceed to part 2 of this section, which focuses on extending these results to a larger and more diverse set of geometries. So this work is described in the Automate paper from RSS 2024, also led by our intern Bingjie Tang. This actually has an unfortunate naming conflict with another paper from UW from, I think, 2021. We discovered this a bit too late, so our apologies about that. So although we were happy with our earlier results, the assemblies we had solved were obviously just a small fraction of the space of real-world assemblies. Fortunately, Autodesk and MIT had at this time recently released Assemble Them All, which is a paper that included the largest assembly dataset to date. We sampled 100 two-part insertion-style assemblies from the dataset and aimed to solve them in this next phase of the work. So as an initial step, we evaluated how well our earlier methods actually worked for these 100 new assemblies in simulation. And the plot shows the distribution of success rates. And unfortunately, the mean success rate was now less than 40%, with very high variance. And this was, to our understanding, due to the increased complexity and sort of geometric diversity of these parts. Yes?
Do you have to finesse the models like you had to finesse the ones, the nut and bolts, or not at all?
That we had to finesse the what?
The 3D models. You mentioned that like there's some art to...
Oh, great question. We did. And the reason is kind of interesting. So when they developed this data set, they actually simulated it in a simulator that relied on penalty-based contacts. So very robust to interpenetration in that sense. Our simulator did not work that way. Now, when we tried to simulate these objects, we often had these very significant contact instabilities. And because these objects were slightly interpenetrating, you couldn't 3D print them and assemble them in the real world. So we did have to do a lot of processing of this data to resolve these interpenetrations and actually have realistic clearances. Yeah.
Yeah. Did you give it back to the community?
Yeah, actually,
Okay.
we communicated with
Meta models, right?
yeah, these are things that you can actually, you'll see 3D printed examples of this. So this is now, this should be publicly available now. If it isn't, and anybody's trying this, just send me an email. Yeah.
Thank you.
So we made our experimental setup also a little bit more realistic, but also more difficult. So we no longer required that parts needed to be placed or bolted on a flat surface. They can now sort of be placed on a foam block, shown here, or in a second gripper, shown here. The image on the right shows a subset of the parts that we assembled, which were all 3D printed in-house, as I mentioned. The parts to be inserted are in white, and the mating parts are in green. So for sim to real on this set of problems, we again aim to achieve at least 80% success rates on 80% of the assemblies, while again being robust to randomized part poses, perceptual noise, control error, as before. So we developed a 3-part solution consisting of automatically generating demonstrations via assembly by disassembly. I'll talk about that. Incorporating an imitation objective into our RL reward formulation, and then selecting the best demonstrations to use at every time step via dynamic time warping. So fundamentally, we believe that our earlier methods were now struggling, in part at least, because exploration was just too difficult on these new assemblies. We wanted to incorporate demonstrations to ease that burden, but acquiring demonstrations for assembly requires either significant human effort or an existing solution. So instead, we use the principle of assembly by disassembly. This is essentially the idea that it's easier to disassemble parts than to assemble them. There's actually a very nice thermodynamic interpretation of this that involves basically disassembly increasing the entropy of the system. And what we did was we initialized parts in their assembled configuration. We grasped the inserted part with a robot, and we pulled the part to random poses using compliant control. And we then reversed the paths to get many valid demonstrations for assembly, as shown on the right. Just note that I'm using the word paths. If you try to reverse velocities or accelerations, the results would be physically implausible, kind of like watching the movie Inception.
But this is still like just nitpicky. Like this
Yeah.
is still assuming invertibility, right?
It is still assuming invertibility of these paths. Yeah.
Like gecko feet or like different kind of stickers.
Right.
You insert them in one way, you have to
Yeah, there's sort of the
remove them in a
asymmetry.
different
Yeah,
way.
yeah.
Okay.
So of course, there was now the question of how to use these demonstration paths in our RL framework. We found that simply imitating these demonstrations was ineffective. It provided very little robustness to part variability, observation noise, and control error. So we incorporated these demonstrations into our RL pipeline. There are many ways to do this, such as the off-policy approach I mentioned at the beginning of this talk. But inspired by Deep Mimic, Jason Peng's work, we chose the simplest solution, which is adding an imitation reward term to our RL reward. At each time step, we encourage the agent to imitate the demonstration path with the highest reward. And this leads to the final question. So for each path, how do we compute that reward? We could just measure the distance between the points on the demonstration path and the path that the robot has traveled. But the demonstration paths were collected for disassembly, not assembly, and have a very different spatial and temporal discretization. But this is a problem that people have thought a lot about. We leverage dynamic time warping, which finds correspondences between points on two paths in order to minimize Euclidean distance, and then returns that distance. At each time step, we just use DTW between the robot path and every demonstration path, and we select the demonstration that is the smallest distance away. We also explored a path signature approach to this for anybody who's interested in that, and it's well documented in the paper. So how well did this method work? Above, you see the original distribution of success rates, and on the bottom is the new distribution, which ultimately hit our milestone of, again, 80% success rates on 80% of the assemblies. Yes? Yeah.
What came first, the results or the 80-80 number?
Actually, the 80-80 number, yeah. It wasn't retrospective, yeah. It motivated us to get to that, yeah, get to that point. But it was stressful, yeah.
Did you notice any common features in the last 20% of tasks?
Over here?
Yeah, which made it.
Yeah, I actually do. Maybe we can return to that at the end, because I have a slide that actually shows some of these sort of the most difficult assemblies, so, yeah. So we return to the problem of sim to real, and on the left, these are video clips of a subset of the sim results, which achieved a mean success rate of 82% over 100 assemblies in 500K trials. And on the right are videos of some of our real-world deployments of the same policies, which achieved a mean success rate of 86.5%. And as before, we deploy the policies also in a full assembly pipeline. We connected our system with NVIDIA's Foundation Pose framework in order to determine the poses of both parts of the assembly. We also implemented a grasp sampling procedure to determine where to grasp the first part. And finally, we executed these policies. So the takeaway of this section is that we could now solve diverse assembly tasks in the real world, more tasks than prior efforts. But I just want to qualify this and say there's so much farther to go. I mean, this is, again, such a small fraction of the space of real-world assemblies. So I think it's just rich with possibilities on solving those problems. So I'll cover the final part of our work in this research effort, which focuses on multimodal sensory observations. This work has been described in 2 papers, Forge, led by our intern Michael Noseworthy, and Taxol from Transactions on Robotics, led by full-time researchers Ireti Akinola and Jie Xu. So here's one point that might surprise you. Although we used vision to initially localize parts in the previous examples, all the policies I've shown thus far actually only use proprioception as input. And although you can technically solve many of these assembly problems without additional sensory inputs, it's neither optimal nor efficient. So I'll now talk briefly about our efforts to do sim to real with force measurements or tactile sensor readings. So starting with force. So at the beginning of the talk, I described nut and bolt assembly as a canonical problem, but then I didn't show you any sim to real examples yet, right? So I'll return to this problem now. On the left is a cross-sectional view of a nut and the top of a bolt. And physically, the most difficult part is getting the threads of the nut and the bolt to engage. If the robot applies any excess force, the nut can slip, which is very difficult to recover from in both simulation and the real world. You can also run into these jamming effects that were mentioned earlier, so, although I don't show it here. So we hypothesized that force sensing would actually enable us to thread nuts and bolts much more reliably and robustly. We proposed a 4-part solution, which consisted of first estimating external contact forces from joint torques. So we didn't use a separate force torque sensor, although it certainly makes sense to do so in the future. Second, we designed the RL policy to take as input a maximum force threshold. Third, we randomized over our controller gains, part friction, and robot dynamics during training. I think the controller gains is kind of maybe the most interesting part there. So you can be robust to setting those gains in the real world. And finally, designing the policy to predict whether it has succeeded in solving the assembly task, which can be used to terminate the policy efficiently or as feedback for actually increasing that force threshold that I mentioned. So the combination of components increased our success rate for this task and others by approximately 32%. It reduced our maximum forces by 22% and reduced our cycle times by 24%. I should show a video here. Okay. So you can't hear it, but there's a satisfying click there. Maybe it's on the live stream. After the threads fully engage, actually a simple open loop controller can be used to tighten the nut to the bottom from this state. So we showed that the same force-based sim-to-real approach could also be used for more complicated tasks, namely planetary gear assembly. These are gear systems that are commonly found in, for example, automobiles, bicycles, and so on. And this requires 8 policies to be executed in sequence. Okay, forgot to play the video, but it's playing now. So for efficiency, we actually interleaved RL policy rollouts with a simple motion planner. The goal being, let's use the right tool at the right time. So eventually it inserts essentially these planet gears, the sun gear, and then it actually tightens bolts afterwards.
So you just use
to real for the actual force in contact.
Contact-rich phase, exactly, exactly. Yeah. Okay, so let's finish with tactile sensing. So one failure mode we often observed is that objects would be physically perturbed once they made contact with their corresponding receptacles, which was very difficult to recover from. And, sorry, okay, there wasn't a question. We hypothesized that tactile sensors could help, as the objects could be observed during grasping and assembly. Among all the tactile sensor types, the robotics research community has seen the greatest interest in visuotactile sensors recently, such as the gel sight. And as a result, we focused on sim-to-real for this sensor. I show a few diagrams and images of the gel sight here. If you're not familiar with it, one quick thing to note is that the gel sight can produce RGB images, tactile images they're called, as well as shear deformation fields by essentially embedding markers into the gel of the sensor. So on the simulation side, we had two parallel paths that we explored, one that simulated tactile images and another that simulated tactile force fields. So in the first path, we used a compliant contact model, which essentially allows objects to slightly interpenetrate each other and generate forces based on Kelvin-Voigt or linear stiffness and damping models. We rendered depth images from an internal camera and then used a learned model to simulate RGB tactile images based on some prior work. In the second path, we also generated an SDF of the object. We queried the SDF at a dense set of points on the sensor surface, and then we used a stiffness and damping model to generate a tactile force field, which is analogous to the shear deformation field on the gel sight, although not exactly identical. We could perform these simulation and rendering steps 200 and 300 times faster than prior efforts. On the learning side, just a very simple addition. So everybody knows that training RL policies from RGB is, of course, a persistent challenge. We developed a simple method where we quickly trained policies with privileged low-dimensional information and then trained a new policy from high-dimensional RGB tactile images while bootstrapping from our previous critic. So I'll show some videos of sim-to-real. On the left, the robot is performing a peg alignment task where the robot has to keep a cylindrical peg perpendicular to the blue surface. The user perturbs the peg, and the robot can react appropriately. On the right, the robot is performing an insertion task, but as you'll see, the lights are shut off in the middle of the rollout. And no surprise, the robot has no difficulty in handling the perturbation since it can use its tactile sensors, which have internal illumination. So now we'll briefly summarize the takeaways and limitations from this series of work, and I'd like to mention some next steps that we have in mind. So, as mentioned before, we can simulate contact-rich interactions. We can use the simulator to learn plausible policies. We can transfer these policies to the real world. We can solve a more diverse set of assembly tasks, although so many assembly tasks left to be solved. And we can leverage force sensing and tactile sensors. But I don't want to give the impression that sim-to-real for robotic assembly is solved. Our standards are high, and we want to fulfill the dream of flexible automation for robotic assembly in a way that could have a lasting impact on modern manufacturing. So let me summarize what we can't do right now. We can't solve problems with large rotation, reorientation, or deformation. Most of the work that you saw so far focused on rigid body insertion, generally speaking with two parts. We can't achieve industry standard success rates with 95% as an absolute minimum target and 99% as an ideal. We can't achieve industry standard cycle times with human level speed as a baseline. Unless you can perform faster than the human or ultimately more cost effectively, it's not going to be adopted in industry. And finally, we can't yet generalize across multitask or out of distribution settings, with the best multitask policy that we achieved in previous work solving around 20 problems with a single policy. So given these takeaways and limitations, what we'd like to build and collaborate on over the next couple of years is a foundation skill for robotic assembly. So I've borrowed this term from Dieter, and in this context, you can think of it as an insert anything or an assemble anything model. So here's a simplified problem formulation. Given a known low-cost robotic arm RGB camera, force sensor, and tactile sensor, a multi-part assembly with a known CAD model of each part. This is a very safe assumption in industrial settings. And a known sequence of assembly operations, which is, again, a very safe assumption in most settings. We would like the model to assemble the parts with robustness to initial pose, appearance, sensor noise, and control error, with 99.9% reliability, and ideally with human-level speed as well. This is quite obviously an ambitious challenge. So in order to achieve it, I believe that these will be some of the key ingredients. The first is scalability. So how do we generate an infinite variety of assembly problems to solve in simulation so that we're not constrained to these existing data sets? Multimodality. How do we simultaneously leverage RGBD sensing, force sensors, force torque sensors, and tactile sensors? Adaptivity. How do we use policies that have already been trained in order to bootstrap learning for assemblies that we have not yet solved? Generality. How do we train policies that can achieve strong performance, not just across hundreds, but let's say thousands of seen assemblies, and reasonable zero-shot performance on unseen assemblies as well? Composability. How do we compose or chain existing assembly skills in order to solve assembly problems involving many parts while preserving high success rates? And fine-tunability. How do we efficiently fine-tune our simulation-trained policies in a real-world robotic work cell in order to get our desired success rates and cycle times as well? So that's all the content that I have for today. For convenience, here are the papers that I've discussed in this presentation. Each paper also contains a link to a project website, which has videos, additional results, and links to lots of code that you can actually try out. There's also real-world deployment code for one of the papers. This is a plug for Isaac Lab. This is the next generation robotic simulation and RL training software that NVIDIA is building. Sort of takes the best of both worlds from Isaac Gym and Isaac Sim. And all major components in this talk will eventually be part of Isaac Lab, hopefully in the near future. And finally, I'd like to say that many people across NVIDIA and academia have been involved in this research effort over the past few years. Some of them for very short periods of time, others for longer. I've listed most of them here in roughly chronological order. And the work would not be possible without all of their key contributions and breakthroughs. Thank you.